We know how to implement the negative feedback system, and the negative feedback amplifier is shown as an example, but every negative feedback system is like this. There is some comparison and integration of that result of that comparison to drive the output. Okay. Now, because this is such a common operation, this entire thing, taking the difference between two quantities and integrating it, that is provided as a standard circuit block, and that's what an op-amp is. Okay. So now, how do you implement this integration? There are only two elements which electrical elements which carry out integration, capacitor and the inductor. And for practical reasons, inductors are too bulky and we can't use them. We'll just use capacitors. Okay. And a capacitor integrates the current flowing through it to give a voltage output. Okay. So now, in this case, our input is also a voltage. So we have to have a way of converting voltage to current that we already know. You know many topologies which do that. So we have this this is the error and this is the output, and omega u is a parameter of the op-amp. It's the unity gain frequency of the op-amp. Okay. So now, how do we implement this? The easiest thing is you have a voltage controlled current source. Let's call it, I mean, the proportionality constant is GM1, and you pass it through a capacitor C1. Okay. What will be the output? What is the output going to be? Yeah. GM1 by SC times VE, which is by definition omega u by S times VE. So this omega u, the unity gain frequency of the op-amp by itself. Okay. Is GM1 by C. Now, of course, the unity gain frequency of the op-amp by itself may not be significant. In the negative feedback loop, what is significant is the unity loop gain frequency. But this is a parameter of the op-amp, and that is GM1 by C. Okay. So we can go ahead and try to implement this. So the capacitor, of course, we can have. So what is a block that we could use? Oh, by the way, before I go further, so let's say we implement it here. And I have C. So will this work as expected? Will this work as expected? Why not? What's the issue? So this resistive divider is also across the capacitor, and it's going to load it. So now, without worrying about implementation, so that we can do the analysis properly without getting distracted ourselves, I will place an ideal buffer here. Later we'll see that this is not quite required. I mean, there are applications where you don't have those resistors and so on, but I'll have this ideal buffer with a gain of 1, so that the transfer function from this VE to the output remains the same as what I have written down on the right side, but it's not affected by loading. Okay. Now, in general, op amps are affected by the load, but that's a complication we can deal with later. Okay. So let's just have this part now. we have the op-amp is basically a voltage controlled current source driving a capacitor. So now this conforms to what we have there, right? So that's it. Looks like the course is over. So we know how to design an op-amp and we're done, right? What complications do you foresee here? How do you implement this voltage controlled current source? How would you do this? Common source amplifier. So common source amplifier, it's okay, but here I need to have two inputs and I want to take the difference voltage between them. I mean, two inputs, neither of which is ground. In the common source amplifier, the source is connected to ground, right? I don't want that. I want two inputs, neither of which is ground, and the current should be proportional to the difference between those two inputs. So what should I use? What's that? Differential amplifier. Okay. Which circuit exactly? What differential amplifier will be used here? What is the differential version of the common source amplifier? What is that circuit? Yeah. What is the equivalent of this? Again, I assume you know this from analog circuits. So again, it should behave like a voltage controlled current source. What is that? With a difference input. Of course, you will use a differential pair. And then what load will you use? Huh? What will you use load? Oh, just this. This is the differential pair, right? And then we'll just connect the capacitor like this. So what should I use on top? You have to use a current mirror. Okay. So that is when this is equivalent to so if you have this, and assuming all transistors are in the active region, this will be around some common mode voltage. I assume these are familiar quantities, common mode voltage, yes or no? Okay. So what will be the incremental current flowing here? So first of all, let me call this 2I0. Okay. At the operating point, you will have I0 and I0. And if you apply these increments Vd by 2 and minus Vd by 2, what will be the incremental current in M1 plus Gm1 Vd by 2, and this will be minus Gm1 Vd by 2, and his output current will be Gm1 Vd. Okay. Let me use lowercase when I denote GMs of transistors. So this whole thing is equivalent to transconductance Gm1, where Gm1 is the transconductance of either M1 or M2 at the operating point. Okay. So this is an op-amp, differential pair loaded by a capacitor. Okay. So is this it? What difficulties do you foresee here, or what will go wrong if you mismatch? Okay. So whenever you make a current source, what is it that you would expect? What is an ideal current source, and what's the common non-ideal feature that you expect? Output resistance, right? Ideal current source should have infinite output resistance. Real current source, whether it is controlled current source or independent current source, it will always have a finite output resistance. So what is the model of this differential pair? The incremental model, what is it? I have, let's say the input is Vd, as I have shown here. You will have a controlled current source GM1 VD, and then what else? You will have an output resistance or output conductance, and what is the output conductance value? So it is GDS1 plus GDS3. Okay. So now, whenever I have differential circuits, right, it's of course assume that M1 is matched to M2 and M3 is matched to M4. Okay. So I'll use the same notation to denote small signal parameters of these. That is, M1 and M2, I'll call it GM1 or GDS1, and similarly M3 and M4, I'll use GDS3 or GDS4 to denote their output conductances. Okay. So one thing that you can expect is of course you make an ideal, you make a controlled current source, but that always comes with a finite output resistance or a non-zero output conductance. Okay. So the problem is okay. Oh, let me not do the transistor level. It's just too messy to draw. By the way, this transconductance, right? Very commonly used symbol is this. Okay. So if you show something like this, it means you have VD and GM1 VD flows out. And you could also indicate the output conductance just below that. That means that it has also a non-zero output conductance. Okay. So first, let me show it with the control source symbol, but after that, I'll stop using that. Okay. Here I use VE, and this one, let me call it RO1, whatever it is. It depends on the circuit, and in this particular case of our differential amplifier, it is 1 by GDSP plus GDSN. Okay. So what is the issue here? Fine, we have an output resistance. So what? What happens? Oh yeah, I forgot the integrating capacitance C1. So we have a resistance RO1. So what's the big deal? Yeah. So what? Huh? No, I know. Why don't I want loading? Yeah, okay. So what? What is the consequence on this? What was the, let's say Vi is 1 volt and the output should be, if K equals 5, it should be 5 volts. Okay. So this is our amplifier, right? That's what I mean. Our closed loop amplifier should have a gain of K. Why did it have a gain of K? In steady state, the feedback drove the negative feedback was such that VFB is driven to be equal to Vi. Okay. So then the output will be equal to 5 volts if K is 5. So now tell me what, if anything goes wrong with this. Yeah. So basically, of course, you can evaluate the transfer function and all that. We'll do it. But what happens is, what do you expect now? in with a DC input, the output steady state should be DC, right? And of course, this voltage here is exactly same as the output, right? Because it's just a buffer. So now, but if you have any non-zero voltage here, some current will be flowing through the resistor. Where will that current come from? From the capacitor. Okay, if the current is flowing through the capacitor, it's not steady state, right? What is, if you have DC steady state, what does it mean? When you have DC, I mean constant signals and steady state, it means that the capacitor currents are zero, inductor voltages are zero in any circuit. Okay, that's how, I mean, you can simply remove all the, I mean, open circuit all the capacitors, short circuit all the inductors, and do DC analysis, right? So it won't come from the capacitor. So where was it come from? Not that many places here. It has to come from the transconductor. So okay, so now it comes from the transconductor. Then what? Exactly. So now the only way this will produce a current is if its controlling voltage is non-zero. Okay. So this means that VE will be non-zero, right? See, the idea was the negative feedback should drive VE to zero. Now it cannot do that. Okay. For any non-zero output voltage, VE will be non-zero. Okay. So this is steady state error, right? So there has to be some current flowing there, which is basically V naught by RO1, and that has to come from this transconductance. So you need a voltage here, which is V naught by GM1 RO1. Okay. So your virtual short is not a perfect short anymore. It has some voltage. It has a small voltage, depends on the value of GM1 RO1, but nonetheless it has some voltage. Okay. So this is steady state error. Okay. The steady state error in the feedback voltage is basically V naught by GM1 RO1. Okay. Now, if we assume that the error is small, okay, the output voltage will still be somewhat close to K times Vi. So we can approximately write this as Vi by K times GM1. Sorry, V naught by GM1 RO1. So K times Vi by GM1 RO1. Okay, approximately that is the steady state error in VFB. Okay. So this means that basically the feedback voltage is not exactly following the input and the output will have some error. Okay. So now let's do the transfer function stuff and see what is the transfer function now? What is the closed loop? What is the, now if you call this the Opamp, right, including that resistance. So ideally the Opamp's transfer function V naught by VE was omega U by S. So what will it be now with this? What is the transfer function of the Opamp? Yeah. What will it be? Please calculate. It is just, yeah. It's basically the current GM1 times VE flowing through the parallel combination of C1 and RO1. Okay. It can be written in many ways. Okay, or you can also write it as okay. So this, by the way, this if you don't make it specific to the circuit, I can just write it as A naught by 1 plus S by P1. Okay, and this P1, what is the value of P1? P1 is omega u by A naught. Okay, because A naught is GM1 RO1, P1 is 1 by RO1 C1. So, and omega u is GM1 by C1. From all of this, you will get that. Okay. So here, this is a slightly different form. Essentially, this is the ideal part, and you get some extra there. So that's what this is telling you, right? Okay. So you have some finite gain A naught, and then a pole at P1, right? Now, what is the closed loop transfer function? Of the amplifier. That is just the op-amp. What we calculated was the transfer function of the op-amp. What is it going to be? By the way, this form can also be written as 1 by S by omega u plus 1 by A naught, right? What is it? Huh? Minus K. Where did minus K come from? What is this? Where is the, then it's not negative feedback at all, right? Why? So there are many different forms in which you can write it. See, so it will be K times A of S by 1 plus, sorry. Okay. This is the general form. You can just derive it. Again, we have gone through all these circuits, so that's why I'm going, I'm not doing this step by step, which can also be written as K 1 by 1 plus. This form is sometimes convenient because L of S has only poles. So the denominator of L of S just appears there. Okay. So what is L of S in this case? What is the loop gain? It is A naught by K 1 plus S by P1, right? It's basically the transfer function of the op-amp divided by K. Okay. It can also be written as 1 by S K by omega u plus K by A naught. Okay. So if you use this form, it's very easy to write this as K divided by 1 plus K by A naught plus S times K by omega u. Okay. So now what is the DC gain, that is the DC gain, right? So obviously S equal to 0 for DC. So the DC gain is no longer K, it is K by 1 plus K by A naught, okay? And if you look at the relative error, that is K by A naught, right? Instead of 1 in the denominator, you have 1 plus K by A naught. So that's the relative error. Now, what is this? Basically, this is the relative error, and you can see that DC relative error is simply 1 by L of 0, right? That is, it is inverse of the DC loop gain, okay? So this is what loop gain does. The higher the loop gain, the smaller the relative error will be. The higher the loop gain, the better the virtual short. That is, the smaller the voltage bit error voltage VE. Okay, and this works at individual frequencies also. If the loop gain is changing with frequency, at different frequencies you will have different sort of virtual short voltages. And if you have very high loop gain at some frequency, you will have a small voltage. Okay. So this we saw already here, right? So we saw that this the error in VFB, basically this VE is VI times K by GM1 RO1. That is VI times K by A naught. So that's the relative error that you see here also. Okay. So this form where you have this omega u, this is a good thing to use, especially for this circuit, because if you plot just the transfer function of the amplifier, that is the magnitude of A of S versus omega, ideally what do we have? We have a single line with minus 20 dB per decade slope, and it crosses unity at omega u. Okay, so this corresponds to RO1 equals infinity. For finite RO1, what will you have? Let's say you have exactly the same GM1 and C1, but you just add RO1. What will change here? Huh? Starts with a DC gain of some other DC gain. Okay, this is A naught, which is GM1 RO1. And then after that, so it's again useful to look at the circuit and understand that at low frequencies, at very low frequencies, this just goes through RO1, the current, and the gain of this is constant, GM1 RO1. At high frequencies, all of this current goes through C1. So it's the same as before. So you expect the high frequency transfer function to be exactly the same as before. Okay. So this part will be the same, and you will have that. Okay. And this breakpoint is P1, which is omega u by A naught. And this makes sense, right? Because here the gain has fallen from A naught to unity. That is a factor of A naught. So because this is minus 20 dB per decade, it's just inversely proportional to frequency. So this has to go up also by a factor A naught. Okay. So these are all things you need to know so that you can calculate things quickly. And in general, in an op-amp, we don't specify P1. Okay, we specify the unity gain frequency and we specify the DC gain. You can specify any two of the three, but typically this is what is specified. Okay, because if you have a different R0 or R01, so essentially you will get that. So that part remains exactly the same. Okay. So the behavior at these high frequencies is not affected. The behavior at DC, the finite output resistance of the transconductor gives you a DC error or a steady state error. In the control systems parlance, it's called steady state step error, right? So the step response doesn't reach its ideal value, but it goes to something different from that. Okay. So the negative feedback works the same as before. That is, if V out is different from VI, there will be a current which partially flows through the capacitor and it keeps on increasing the voltage. But somehow this current is stolen by the resistor, so it doesn't go all the way to the ideal value, but it goes to something less than that. Okay. Any questions here? So again, very simple circuit. The transfer function is first order, but again, the important thing is to understand what's going on inside the circuit. Okay. So this is the gain of the op-amp itself, and the loop gain, of course, follows a similar behavior. If I just plot the loop gain, maybe I'll do it here. In this particular case, it is A of S by K. So what happens is, ideally, this would be the unity loop gain frequency. Now with the finite output resistance, you will have something like this, where the DC loop gain is A naught by K. The pole remains wherever it was, because you're just like dividing by K. That doesn't change the pole frequency. But the unity loop gain frequency is omega u by K. Okay. So similarly, if you have a different resistance value, but the same capacitance value, only the pole changes. The unity loop gain frequency doesn't change. Okay. So what does this mean? If you apply a step, that transient, that is because of the capacitor, right? So that by and large remains the same. Okay. So you are getting that exponential, it remains the same. Where the exponential settles to, that's what is changed by this resistor. Okay. So this is useful to understand all this, because as circuits get more complicated, you don't want to throw everything in the model. Okay. If you do that, you will get something very complicated, which is very hard to interpret. So now if you are asked to comment on the transient response of this, I think you can safely say that it is more or less the same as what you would have without that resistor. Only thing is, it's only the steady state value that is changed. Okay. This is fine. So we will have to, I mean, the circuits will get more and more complicated, and we should have ways of analyzing them. But I'm assuming you have seen the analysis of all of this. That is op-amp with finite gain. Have you or have you not? You have. Okay. Fine. So now, of course, here the problem is that, of course, this DC gain may or may not be large enough. Now it turns out, what is the DC gain of our differential pair with the current mirror load? It was GM1 by GDS1 plus GDS3. Basically, it's of the order of GM by GDS of a MOS transistor. Okay. So now this is an inherent property of the MOS transistor, and this increases as you increase the channel length, right? For a given bias current, what is GM? GM is square root of 2 mu Cox W by L times I naught, where I naught is the bias current, and GDS is lambda times I naught. Okay. So you can see, first of all, and lambda itself is inversely proportional to L, right? Okay. So how do you increase this? You can increase this by increasing the length of the transistors. Okay. Now, of course, that comes with, what's the disadvantage of increasing the length? What is the disadvantage of increasing the MOS transistor length? Larger parasitic capacitors, right? All the parasitics will be larger proportionately. Okay. So that is a problem. In fact, if you increase the length to increase the DC gain, to keep the GM the same, you have to increase W also. Okay, this is assuming square law. If you have if you are operating in weak inversion, it behaves differently. But anyway, this is what it is, right? And then, of course, if you operate with a small current density, you will tend to have a higher DC gain. Okay. So one way, if you have, of course, you make this and you find that the DC gain is not sufficient. Yes. So then you can try to increase the length. Okay. But let's say, and also it's good to have an idea of how much the GM by GDS is. It depends on the transistor. But if you take the minimum length transistor in any given process, in modern processes, this may be of the order of 10 or 20 or something. It's not a very large number. What is the gain that you want from an op-amp? Infinity. Of course, you won't get infinity, but you want large values, right? So typically with a single stage, you may not get a large enough value. So we have to change the topologies in some way. Increasing the length works, but if you have a gain of 20 and you want to make it 200, this is probably not a great idea, because then you have to increase the L by such a large factor, and W also, the circuit just bloats up, and it probably becomes so much slower that it's useless. Okay, so you have to find other ways of increasing the gain. Okay. So this is what is this is a single stage op amp. We'll go into the circuit level analysis of this, of all its different parameters like mismatch and noise and so on. You're already familiar with the swing limits, etc. We'll just review them, and the mismatch and noise we'll look at. But before that, I want to go through the different topologies at the level of the control sources. Okay, so that is always useful. I find it less distracting, because if we mix up transistor level details with the system level details, it is confusing. So we'll first do everything with control sources and then go to the transistor level details. Okay. But if you the simplest op amp is simply a transconductor driving a capacitor that behaves like an integrator. The only problem is any transconductor you make will have a non-zero output conductance or a finite output resistance. So that limits the DC gain. So that means if you apply a DC input, the output will not be exactly what it's supposed to be. It will be slightly different from that. This is because of the steady state error. And the larger the DC gain of the op amp, the smaller the steady state error. But there are limits to how much you can increase. With this sort of single stage op amp using MOS transistors, you will get essentially the inherent gain of the MOS transistor, the MOS common source amplifier, as your gain. Okay, that may not be sufficient. Now, this is technology dependent, but in modern processes, this is what you get. Okay. So now, if you want to increase the gain by a small amount, and you do this also, anyway, it's not that you always use just one technique, you combine different techniques. When I say L, you have to look at the output conductance of PMOS and NMOS both, and see whichever is limiting, you have to increase it. You may have to increase the length of both transistors. And because you increase the length for the same current, you may have to increase the W also. Okay. So basically the area goes up. If you increase L by 10 times, the area goes up by a factor of 100. Okay. So large increases are not possible. So what can be a strategy to increase the gain? What all can we do? Add one more. So our negative feedback loop has an integrator, right? So we want to have an integrator, but with a higher DC gain. So how do we do that? Huh? Yeah, but how much will you reduce it? It will also affect other things, right? Because if you change the you want to change only A naught, because if you change I naught, the GM also will change, and then the unity gain frequency will change, right? Okay. which our input? So, but basically that may work. We'll come to that later, but that's not, then you don't have an integrator anymore, right? How? Yeah, you will decrease R so much and then you will not have any gain in that. How? Yeah, so that is one of the possibilities. You have a current controlled current source or a common gate amplifier. So essentially it gives you the same output current as the input current, but its output resistance is much higher. So that is definitely one possibility. Okay. So we will look at that. That gives you like a class of op amps. And then there are other things as well that we can do. So the way we were getting this integration is by, so this input voltage is converted to current by this, and then that current is converted to voltage by connecting the capacitor across it. Okay. So now this current to voltage conversion maybe we can do in a different way. Okay, because right now the main problem is that the voltage across the capacitor also appears across the output conductance, right? That's why it is drawing current. If we somehow do this current to voltage conversion without that output voltage appearing across the resistor, we may have a better topology. We'll see. So these give rise to different op-amp families. And also another thing might be you look at how much current is flowing through RO1, and then you make another current source which compensates that exactly, right? So that will give you another set of op-amp topologies, right? So logically you can derive like many things and then we'll go to that. Okay. Any questions? Okay then. See you all.